Hello everyone. Today we are going to derive the stress-strain relationship matrix for a three-dimensional finite element. It is important to derive the stress-strain relationship matrix for a three-dimensional finite element to understand the concept of plane strain conditions, and also the derivation for the stress-strain relationship matrix for plane stress conditions would be very easy if we actually derive this matrix for three-dimensional elements. There is a little bit of background life here, so please excuse me. I would recommend you not to use the headsets as you listen to this video. Maybe you could use a speaker. Now, before we get straight into the business of the derivation, it would be a very good idea if we actually recapitulate the concept of Poisson's ratio. Most of you should be conversant with the concept of Poisson's ratio. Nonetheless, it would be a very good idea if we recapitulate the concept of Poisson's ratio. And also note that this stress-strain relationship matrix is also called as a constitutive matrix. So they are used interchangeably. So to begin with, let me first draw a cube to define the Poisson's ratio. Just imagine a cube. And let us subject this cube to a stress along the y direction. It is subjected to a normal stress along the y direction. So sigma y indicates that it is a stress that is acting along the y direction. Sorry, excuse me. Okay. Now, you know very well that if it is pulled on either side, obviously the length along the y direction is going to increase, but what about the dimension along the x direction and the dimension along the z direction, right? The length of the cube is actually going to decrease, which means that I'm talking about this length. It is actually going to decrease. And also this particular length, maybe if you want, you can call it as a depth, that is also going to decrease. So both the depth as well as the breadth of the cube is actually going to decrease. Okay. Now, which means that there is also strain that is produced along the z direction. We can call this as the z direction. And there is also strain that is produced along the x direction. So the strain is actually produced along three directions. One is the y direction, x direction, and z directions. Okay. Now I'm going to call the strain that is produced along the y direction, where the force is actually acting, sigma y is actually acting, as the longitudinal strain. Okay. So it is the longitudinal strain. So longitudinal strain is the strain that is acting along the y direction. And the strain that is acting along the x direction, as well as the strain that is acting along the z direction, we can call that as the lateral strain. So these are strains that are acting along the x direction, as well as the strain that is acting along the z direction. We call that as the lateral strain. We know very well what is strain. It is going to be change in length divided by original length. So let me also represent that. Maybe I can call the height as L, okay, and I can call the change in length as del L. Now I can define longitudinal strain as change in length divided by original length. So longitudinal strain is going to be change in length divided by original length. Okay. I can also define lateral strain because the dimension along the x as well as the dimension along the z direction, they are also changing. The breadth is changing, the depth is changing. So we can say that those strains are called as the lateral strains. I can also define that. So lateral strain is equal to change in breadth divided by original breadth, or you can say it is the change in depth divided by original depth. Okay, so these two are lateral strains. Now, one thing that you have to notice there is when the dimension along the y direction is increasing, the dimension along the x and z, they are actually going to decrease, which means that since those dimensions are decreasing, we can clearly say the lateral strain will be compressive if the longitudinal strain is tensile. So I'm introducing a negative sign to indicate that there is going to be a compressive strain. The converse is equally true. If the longitudinal strain is going to be compressive, then the lateral strains will be tensile. It is experimentally verified before the elastic limit. The ratio of the lateral strain to the longitudinal strain is always a constant. So it is experimentally verified. So I can say within the elastic limit, it is experimentally verified. That the ratio of the lateral strain to the longitudinal strain is always a constant. So you can say that it is because they did the experiment, and after repeated measurements, they came to the conclusion that the experimentalists come to the conclusion that the lateral strain, the ratio of the lateral strain to the longitudinal strain is always going to be a constant. And this constant is denoted by the notation nu. So that is the constant. Some textbooks use the notation mu, but let us use the notation nu for the Poisson's ratio. It is the ratio of the lateral strain to the longitudinal strain. Okay. Sometimes for shear strain, they use the notation nu, but no problem. Sometimes they also use the notation mu, right? Both are used. Some textbooks use the notation mu. Maybe I will stick to the notation mu here. Okay, it is a Poisson's ratio, which is lateral strain divided by longitudinal strain, and lateral strain is always going to be negative if the longitudinal strain is positive. Now it enables us to write the lateral strain in terms of longitudinal strain. So I can now say lateral strain in terms of longitudinal strain. So lateral strain along the x direction, is equal to mu times longitudinal strain along the y direction. Of course, the strain due to the load that is acting along the y direction, the strain along the y direction because of the load that is acting along the y direction, that is what is called as the longitudinal strain. Okay, so we can also write this expression this way, and because the longitudinal strain is positive, in our case this will be negative. Okay, so this is the lateral strain along the x direction because of the load that is acting along the y direction. We can write the statement like this. Maybe in the next step I can write it even more clearly with using the mathematical notations. We can write that is the lateral strain along the x direction. Okay, the lateral strain along the x direction, we can say the strain along the x direction, because there is going to be strain along the x direction because of the load acting along the y direction. So the net strain along the x direction is going to be equal to minus sign mu into longitudinal strain along the y direction. Okay, it is the longitudinal strain along the y direction. So this is the longitudinal strain. All right, we already have this equation that Young's modulus is actually longitudinal stress divided by the corresponding longitudinal strain. Since we have this relationship, because the longitudinal stress is acting along the y direction, the longitudinal strain also acts along the y direction. So that enables us to write the equation for the longitudinal strain along the y direction as longitudinal stress along the y direction divided by Young's modulus. Now what I'm going to do is I'm going to take this equation and I'm going to substitute it here to write the strain along the x direction as minus mu into sigma y divided by E. Okay, so in exactly the same manner, I can write the strain that is produced along the z direction can also be written as minus mu into sigma y divided by E. This is the strain that is produced along the z direction. Okay. Now let us go to case 2. In case 1, there is only one stress that is acting, which is acting along the y direction. Now let us move on to case 2. Okay, in case 2, we are going to consider a cube that is subjected to two mutually perpendicular stresses. So first, let me represent the stresses acting on the cube. So it is a cube that is subjected to two mutually perpendicular stresses. One is sigma x that is acting along the x direction. This is the normal stress that is acting along the x direction. Another one is sigma y, which is the normal stress that is acting along the y direction. Okay. Now I'm going to find out the net strain that is produced along the x direction. Okay. So let me write that. So the net strain that is produced along the x direction is given by the strain due to sigma x along the x direction. Okay, the direction is fixed. We are interested in finding the strain along the x direction plus the strain due to sigma y. Now the strain due to sigma x acting along the x direction, that strain will be longitudinal strain. And the strain due to sigma y along the x direction, you see the strain is produced along the x direction because of the stress acting along the y direction. That will be lateral strain. All we have to do is substitute the equations that we have already derived for longitudinal strain and substitute the equations that we have already derived for lateral strain. Okay. So that will give us the net strain that is acting along the x direction. So here we go. The net strain acting along the x direction is longitudinal strain formula is longitudinal stress divided by longitudinal stress divided by Young's modulus. Okay, so in that case it will be sigma x divided by E. And the strain due to lateral, which means the lateral strain, is given by this equation. It is mu times the longitudinal strain acting, in our case, along the x direction. Because there is a negative sign, I use the negative sign, mu times the longitudinal strain along the y direction. Okay, fine. So this is the lateral strain and this is the longitudinal strain. So this gives the net strain along the x direction. So in case there is a third stress that is acting along the z direction, then the stress that is acting along the z direction, that can be sigma z, will also produce a strain along the x direction, will also produce a lateral strain along the x direction, in which case I have to include that term also. It will be minus mu into sigma z divided by E. Okay, so this is the expression for the net strain that is produced along the x direction. In exactly the same manner, I can now write the net strain that is produced along the y direction. That will be sigma y by E minus mu into sigma x by E minus mu into sigma z divided by E. Similarly, net strain that is produced along the z direction can be written as sigma z by E minus mu into sigma y by E minus mu into sigma x divided by E. I can rearrange these equations. I can rearrange them in the form sigma x minus mu into sigma y minus mu into sigma z is equal to capital E into net strain acting along the x direction. Similarly, I can write minus mu into sigma x plus sigma y minus mu into sigma z is equal to capital E into the net strain that is produced along the y direction. Similarly, it's going to be minus mu into sigma x, it's minus mu into sigma y plus sigma z is equal to capital E into net strain that is produced along the z direction. Okay, now what I will say is I have three equations now. Equation 1, 2 and equation 3. I'm going to solve the three equations for the three unknowns. The unknowns here are sigma x, sigma y, sigma z. So instead of calling that as sigma x, sigma y, sigma z, I will call this sigma x as A. I'll call the sigma y as B. I'll call the sigma z as C. And I'll call this entire term as alpha. I'll call this term as beta. I'll call this term as gamma. And I'm going to rewrite the three equations so that those equations can look a little bit less intimidating. Okay, so let me rewrite the three equations again. So here we go. The equations will look like A minus mu B minus mu C is equal to alpha minus mu A plus B minus mu C is equal to beta minus mu A minus mu B plus C is equal to gamma. So I have three equations for three unknowns. So I'm just going to solve the three equations for the three unknowns, and I am going to substitute the values for A, B and C back into the equations. Okay, now we have three equations for three unknowns, A, B and C, where A is sigma x, B is sigma y and C is sigma z, and alpha is capital E small e suffix x, beta is capital E small e suffix y, and gamma is capital E small e suffix z. But capital E stands for the Young's modulus and small e stands for the strain. The suffix x denotes the normal strain along the x direction. Suffix y indicates the strain, normal strain along the y direction, and the z indicates the normal strain along the z direction. All right. Now, in order to solve these three equations, I can see very clearly that I can immediately cancel the C term for the first two equations if I just subtract the second equation from the first equation. So let me do that. So let me try 1 minus 2. If I just try 1 minus 2, I'll be getting 1 plus mu into A minus mu B minus B is equal to alpha minus beta. So I have cancelled the C term here. Okay. Now I can just pull minus B outside from this equation. I can write it as 1 plus mu into A. If I just pull that minus B outside, okay, I have pulled minus B outside, I'll be getting it as 1 plus mu, right, is equal to alpha minus beta. So this is going to be my star equation 1 because it has got two unknowns, A and B. If I can get one more equation in terms of two unknowns, A and B, I can solve the two equations to get the values of A and B. So I'm going to get star equation number 2, solve the two star equations to get the values of A and B. All right. So the next equation is I'm going to solve equation number 1 and 3. And I'm going to cancel C. So what I will do, let me first solve 1 and 3. So I will write the first equation as it is. So I can say first equation is simply multiplied by 1. I will be getting A minus mu B minus mu C is equal to alpha. So first equation is simply multiplied by 1. And the third equation is multiplied by mu. Okay. So the third equation is multiplied by mu. If I multiply the third equation by mu, I will be getting minus mu square A minus mu square B plus mu C is equal to mu times gamma. Now I can simply add these two equations to cancel the C term. So I'll be getting, if I add these two equations, I'll be getting 1 minus mu square into A. If I simply add these two equations, I can just bring the minus B outside this equation. I'll be left out with the mu plus mu square into B. Cancel the mu C, minus mu C and plus mu C. I will be getting alpha plus mu times gamma. So that's going to be my star equation 2. Now I have to solve the two star equations. In order to solve the two star equations, let us say that I want to cancel B. If I want to cancel B, I have to multiply the first star equation here. I want to multiply the first star equation by mu. In that way, before the coefficient of B now becomes mu plus mu square. In star equation 2, you have the coefficient of B as mu plus mu square. Now it becomes easy for me to solve. So let me multiply star equation 1 by mu. So I'll be getting, if I multiply star equation 1, I'm just going to hit it with mu. I will be getting mu plus mu square into A, mu plus mu square into A. If I hit it with mu, I'll be getting minus mu plus mu square into B is equal to, hit it with mu on the right hand side, I'll be getting mu times alpha minus mu times beta. So this is the equation when you hit the star equation 1 with mu. Now I can simply subtract the 2 in order to cancel the equations. I can just simply subtract them. Okay. If I simply subtract the 2, what I will be getting, I'll be getting 1 minus mu square minus mu square into A. Well, if I just subtract them, these two terms will cancel each other out because minus plus they cancel, right? let me do the right hand side. I'm just going to subtract the 2, and let me bring the coefficient of alpha outside. I'll be getting 1 minus mu into alpha. So subtract the 2 plus mu beta, that's what you will be ending up with, plus mu beta. And plus mu gamma minus 0, it's simply plus mu gamma. All right, so now I can get the value of A. I can see the value of A. So in the next page I will write the value of A. So here we go. A is equal to 1 minus mu into alpha plus mu into beta plus mu times gamma divided by, it is 1 minus 2 mu square, minus mu square minus mu square is 2 mu square minus mu. So it will be 1 minus 2 mu square minus mu. So that's the value of A. Now I'm just going to make one change here. That change is, can I write mathematically, I can write minus mu. I can write this minus mu as minus 2 mu plus mu. Not surprising, I can write it. So what I will do is, I will simply write this minus mu here as minus 2 mu plus mu. Allow me to do that. I'll be writing it as minus 2 mu plus mu. Okay, if I can do that, I can actually pull minus 2 mu outside from these two terms. So that's what I'm going to do in the next step. A is equal to 1 minus mu times alpha plus mu times beta plus mu times gamma whole divided by 1. I can pull minus 2 mu outside from these two terms. I'll be left out with mu plus 1 plus mu. So that's what I will be left out with. So in the next step, A is equal to 1 minus mu into alpha plus mu times beta plus mu times gamma whole divided by, I can see that I can write this term as 1 plus mu, let me put the bracket, I'm writing these two terms first, minus of 2 mu into mu plus 1 can be written as 1 plus mu. Just making things, let us do the things as clear and explicit as possible. It's going to be 1 minus mu times alpha plus mu times beta plus mu times gamma divided by, I can bring 1 plus mu outside from these two terms. I'll be left out with 1 plus mu. If I take it outside, I'll be left out with 1 minus 2 mu. All right, because I'm just bringing 1 plus mu outside, I'll be left out with 1 minus 2 mu. Okay, so this is my value of A. Okay, 1 minus mu into alpha plus mu times beta plus mu times gamma divided by 1 plus mu into 1 minus 2 mu. Let me now substitute what A, alpha, beta and gamma in this equation. So if I can do that, A is sigma x, normal stress along the x direction, 1 minus mu into alpha is capital E suffix x plus mu into beta is capital E suffix y plus gamma is capital E suffix z whole divided by 1 plus mu into 1 minus 2 mu, 1 plus mu into 1 minus 2 mu. Right, now I can further write this equation as, I can bring the capital E, which is common, outside this equation. I can write it as capital E divided by 1 plus mu into 1 minus 2 mu. Okay, into 1 minus mu into Ex plus mu into Ey plus mu into Ez. Okay, so this is the equation that gives me the value of the normal stress along the x direction. In exactly the same manner, you can get the value of the normal stress along the y direction, in which case it will be like capital E divided by 1 plus mu into 1 minus 2 mu into mu into Ex plus 1 minus mu into Ey plus mu into Ez. I can write the value of sigma z as capital E divided by 1 plus mu into 1 minus 2 mu into mu into Ex plus mu into Ey plus 1 minus mu into Ez. So I can write it this way. So I have got the value of sigma x, sigma y, sigma z. That is the expression. See, you can clearly see that there is expression. What we have got is the expression that is trying to relate the normal stress on the normal strains. Okay, normal stresses and the normal strains. Similarly, I have to come up with the equations that relates the shear stresses and the shear strains. That's what I'm going to do in the next step. So I can call the final equations here as equation A, equation B, equation C, and I will also get equations D, E, F, that is for the shear stresses. Okay, so let me try that. Again, first let me represent the shear stresses produced in a cube. So I can just symbolically represent that. Just imagine a cube. And let me entail a set of coordinate axes on this cube. This is going to be my x-axis. This is my y-axis. This is my z-axis. Okay. And the shear stress that is produced on this plane, let me shade it as the red in color. And if you want to talk about this plane, it's the shear stress. The symbol for shear stress is tau. And since you are talking about that plane, it is the plane that is perpendicular to x-axis. And let us say that you are talking about the shear stress that is taking place along the y direction. Okay, y direction. So in that case, it will be y, tau xy. So the first letter suffix indicates the plane. Okay, it is a plane that is perpendicular to x-axis, and the green color indicates the direction, that is the y direction. Okay, similarly you can define the shear stress on this plane, in which case the shear stress is tau, and it is taking place on a plane that is perpendicular to y-axis. And let us say that you are bothered about the stress along the shear along the x direction, so you can write tau x. Similarly, I can write for all the shear stresses, but you know, because of complementary shear stresses, tau xy is equal to tau yx, so I don't have to write two separate equations for them. Okay, now we know, I would like to start with the shear modulus. We know what is shear modulus. Shear modulus is shear stress divided by shear strain. I'll consider this shear and the corresponding shear strain. Okay, now I can write immediately the expression for shear stress. Tau xy is equal to C into nu xy. I can just draw a box around this equation. Now you learnt it in your strength of materials, the relationship between Young's modulus and shear modulus, and that relationship is E is equal to 2C into 1 plus mu. That is the equation that establishes the relationship between Young's modulus and shear modulus. I can now write the value for shear modulus. Shear modulus C can be written as capital E divided by 2 into 1 plus mu. You see, in each of the normal stress equations, you are left out with capital E divided by 1 plus mu into 1 minus 2 mu. I want to bring exactly the same term, same coefficient outside. So first thing that I will do is 1 plus mu is already there. So I will multiply and divide by 1 minus 2 mu. In that way, I get this term, capital E divided by 1 plus mu into 1 minus 2 mu. So since I have got this term, I'll be left out shear modulus is going to be capital E divided by 1 plus mu into 1 minus 2 mu into 1 minus 2 mu divided by 2. So I'm going to plug the expression for shear modulus in this equation. So in the next step, I can write the expression for shear stress tau xy is equal to capital E divided by 1 plus mu into 1 minus 2 mu into 1 minus 2 mu divided by 2 into nu xy. This can be our equation D. In exactly the same manner, I can write the expression for tau xy, tau yz, in which case I'll be getting capital E divided by 1 plus mu into 1 minus 2 mu, 1 minus 2 mu divided by 2 into nu yz. So that's going to be my equation E. I can also get the expression for tau zx or xz. Tau zx is equal to capital E divided by 1 plus mu into 1 minus 2 mu into 1 minus 2 mu divided by 2 into nu zx. So that's going to be my expression F. Now I have three equations A, B, C that establishes the relationship between normal stresses and normal strains. And I also have equations D, F that establishes the relationship between shear stresses and the corresponding shear strains. Now I have six equations A, B, C, D, E, and F. I'm going to write these six equations as a single matrix form, in a single form of a matrix. I'm going to write these six equations. So let me see how I can do that. So in the next step, I am going to write all the stresses on the left side. It is going to be sigma x, sigma y, sigma z, tau xy, tau yz, and tau zx. These are all the normal and shear stresses. And you have the term that is kept outside each of the three equations. So I can very well write the term that is kept outside each of the three equations, which is capital E divided by 1 plus mu into 1 minus 2 mu. There is going to be a 6 bar 6 matrix. It is a matrix that establishes the relationship between stress and the corresponding strain. So let me write the corresponding strains here. The strain corresponding to normal stress sigma x is sigma ex. Similarly, for sigma y, it is ey. For sigma z, it is ez. For tau xy, it's going to be nu xy. For tau yz, it is going to be nu yz. For tau zx, it's going to be nu zx. And writing it in the form of a matrix is easy. All you have to do is first write the coefficient of Ex in equation A. So what is the coefficient of Ex in equation A? It is 1 minus mu. Then you write the coefficient of Ey, which is mu. Then you write the coefficient of Ez, which is mu. Then you also write the coefficient of nu xy, which is 0. Nu yz, it is 0. Nu zx, it will be 0. Because those terms do not exist in equation A. So I'll be getting, so 1 minus mu, 0, 0, 0. So it will be 1 minus mu, 0, 0, 0. Okay, so if I hit this matrix, multiply the first row and the column, I'm going to end up with equation A. So I can very well write it in the form of a matrix. Similarly, if I do for equation B, I'll be getting mu 1 minus mu 0 0 0. Similarly, for equation C, I'll be getting mu 1 minus mu 0 0 0. Now for equation D, what is the coefficient of Ex in equation D? 0. Ey 0. Ez 0. What is the coefficient of nu xy? Well, it is 1 minus 2 mu divided by 2. And the coefficient of nu yz in equation D, it's 0. There is no nu yz term, there is no zx term, so all those coefficients will be 0 except the coefficient for nu xy. So I'll be getting 0 0 0. For nu xy, it is 1 minus 2 mu divided by 2, 0 0. Similarly, I'll be getting 0 0 0 0. 1 minus 2 mu divided by 2, 0. Similarly, all the coefficients will be 0 except the coefficient for nu zx, in which case it will be 1 minus 2 mu divided by 2. Right? So you can see this matrix that establishes the relationship between the stress and the strain. Okay, this matrix that is boxed red in color, that establishes the relationship between stress and strain. It is called as the stress-strain relationship matrix. It is stress-strain relationship matrix. Or you can also call this as the constitutive matrix. Okay, this is for 3D. Now, in order to get the matrix for 2D, we have two conditions in 2D. One is the plane strain condition, the second one is the plane stress condition. You have to follow the same methodology, but for the plane strain condition, this matrix that you see here, this 6x6 stress strain relationship matrix, will be reduced to the two-dimensional situation by applying the boundary conditions. Okay, now how we do that, we will see that in the next session. But this is the matrix for isotropic material that obeys Hooke's law for a linear material, linear isotropic material. For a three-dimensional finite element, the matrix that is under play, the stress strain matrix that is under play, we call it as the D matrix. Okay, the symbol for the stress strain relationship matrix, it is the D matrix. Okay, it is the stress strain relationship matrix. Thank you all for your patience. I appreciate your time. Thank you so much.